Imagine you find a rock. No label, no date, no records, nothing. So, how could anyone possibly know whether it formed 100 years ago, 100 million years ago, or even 4 billion years ago? It sounds impossible. After all, nobody was there to watch it form. And yet geologists can determine not only which rocks are older and younger, but sometimes their actual age. In fact, these methods allowed scientists to reconstruct Earth's history, stretching back billions of years. But here's the twist. The first geologists had no way to determine the exact age of a single rock. So, how did they begin solving the mystery? Enjoy geology and earth science? Subscribe for more. The answer starts with a simple observation made more than 300 years ago. Imagine walking into a canyon. Layer upon layer of rock stretches upward like the pages of a giant history book. At first glance, it's just stone. But early geologists realized something extraordinary. These layers weren't random. They told a story. It is like making a sandwich. You place one slice of bread down first, then cheese, then lettuce, then another slice of bread. The bottom layer is laid first. It couldn't be any other way. The same logic applies to sediments. This idea became known as the principle of superposition. The oldest sedimentary layers are, generally, at the bottom. The youngest are at the top. The principle of superposition is one of the techniques of relative dating, a method used to determine the chronological order of past events without assigning a specific numerical age. But rocks tell us much more than that. And this was only the first clue. Over the next century, geologists discovered more clues hidden in rocks. Suppose you find rock layers tilted, nearly vertical. Could they have formed that way? Probably not. Sediments usually settle in nearly horizontal layers. So, if the layers are tilted today, something must have happened after they formed. This idea became known as the principle of original horizontality. But the clues get even better. Imagine a crack of magma slicing through several rock layers. Which came first, the layers or the magma? The answer is simple. The magma had to cut through rocks that already existed. This is the principle of cross-cutting relationships. Anything that cuts another feature must be younger than what it cuts. Now imagine finding fragments of granite trapped inside another rock. Those fragments had to exist before the surrounding rock formed. This is the principle of inclusions. Using clues like these, geologists could reconstruct a sequence of ancient events. But one major challenge remained. These principles worked well at a single location. But how could geologists connect rocks separated by hundreds or even thousands of kilometers? The answer came from something that had once been alive. In the early 1800s, an English surveyor named William Smith noticed something strange while examining rock layers exposed during canal construction. Certain fossils always appeared in the same order from older rocks to younger rocks. Again and again. Across different regions. It means that some species appeared, thrived, then disappeared forever. And once they vanished, they never returned higher in the rock sequence. This observation became the principle of fossil succession. And it completely changed geology. Some organisms lived for only relatively short periods, but spread across large regions. These became known as index fossils. And for the first time, Earth's history was beginning to come into focus. But then, they stumbled upon something even stranger. Parts of the story were missing. Imagine reading a history book. Page 10 is followed by page 47. Everything in between is missing. That's what geologists discovered in the rock record. At places like Sycamore Point, younger rock layers sit on top of much older, tilted rocks. Something wasn't right. The older rocks had formed, hardened into stone, tilted, eroded, and only then were younger sediments deposited above them. Entire chapters of Earth's history were gone. These gaps are called unconformities, and the missing time they represent is called a hiatus. Suddenly, geologists realized something profound. Earth's history isn't recorded continuously. It's more like a movie with missing scenes. So to reconstruct the full story, they would need evidence from many different locations. That effort eventually produced one of geology's greatest achievements: the geologic column. No single location contains all of Earth's history, but by combining evidence from millions of rock exposures worldwide, geologists built a master timeline known as the geologic column. This timeline divides Earth's history into enormous chapters: eons, eras, periods, epochs. Within it, we see the appearance of the first life, the rise of fishes, the spread of forests, the age of dinosaurs, the age of mammals, and eventually, us. By the early 1900s, geologists had reconstructed the sequence of Earth's history remarkably well. There was just one problem. They still didn't know the actual ages. Then a discovery in physics changed everything. In 1896, scientists discovered radioactivity, and hidden inside that discovery was a natural clock. Every atom contains a nucleus. Some nuclei are stable, others are unstable. Over time, unstable atoms spontaneously transform into different atoms. This process is called radioactive decay. For example, uranium eventually becomes lead. Potassium can become argon. Rubidium can become strontium. Here's the astonishing part. Scientists can't predict when a specific atom will decay, but they can predict how long it takes for half of a large group of atoms to decay. This interval is called the half-life. Imagine starting with 16 radioactive atoms. After one half-life, only 8 remain. After another half-life, 4 remain. Then 2. Then 1. The process is incredibly consistent, like a clock that never stops ticking. And that's when geologists realized something. If you measure the ratio of parent atoms to daughter atoms inside a mineral, you can calculate how much time has passed. For the first time in history, rocks could tell their age, numerically, not just relatively. But when scientists say a rock is billions of years old, what exactly does that mean? Most people assume radiometric dating tells us when a rock formed. Not quite. The clock starts ticking only when atoms become trapped inside a crystal structure. Think of it like locking the doors of a building. Before the doors close, atoms can move in and out freely. Afterward, they're trapped. Now the clock begins. For an igneous rock, a radiometric date usually tells us when the magma cooled and solidified. For a metamorphic rock, it often tells us when the rock cooled after metamorphism. And here's an important twist. Sedimentary rocks are usually much harder to date directly. Why? Because the grains inside them may have formed in older rocks long before the sedimentary rock itself existed. A sand grain might be 1 billion years old, but the sandstone containing it could be much younger. Which means geologists must combine radiometric dating with relative dating principles to reconstruct the full story. It's not one method. It's both working together. Once radiometric dating became possible, scientists finally tackled the ultimate mystery. How old is Earth? Some estimates suggested only millions of years. Others argued for much longer. Then radiometric dating provided an answer. The oldest minerals found on Earth, tiny zircon crystals, are about 4.4 billion years old. Some meteorites date to approximately 4.57 billion years. Moon rocks tell a similar story. Together, these clues point to an Earth that formed roughly 4.54 billion years ago, a number almost impossible to comprehend. Relative dating reveals the sequence. Radiometric dating provides the clock. And together, they allow us to read a history book written, not with words, but with stone. The next time you see a cliff exposing layers of rock, remember, you're not looking at a pile of stone. You're looking at pages from Earth's autobiography. So if you enjoyed this journey through deep time, don't forget to like, subscribe, and join us for the next episode.